Hi everybody, welcome back to Chem 121. Look how close we are to the end. Hee it's right there. And we're going to finish today, so that's great. What do we got on the agenda at the bottom? We have a quiz due tonight, so quiz for Chapter 9 is due tonight. Make sure you get that in by the deadline. That is a soft deadline. You have tomorrow if you need it. Course evaluations, make sure you get those done by Friday. Friday is the hard deadline for that. I can't change that or modify it in any way. Make sure you do it earlier rather than later, in case something comes up. And then the last worksheet on solubility is due next Wednesday. Not tomorrow, but the next Wednesday on June 16th. Any questions, let me know. We're going to finish this off today. Let's talk about the pH scale. So the pH scale is a very important tool that is used to conceptualize amounts of acid. But there's an issue with it that makes it a little bit confusing, and that is it is not a linear scale. So the numbers do not mean like a pH 5 is twice as acidic as some other number, like 2 or whatever. The scale is what's known as a logarithmic scale. And we'll talk about what that means in just a second. So the pH of a solution is the measure of how much H plus is in solution. In other words, we are measuring how acidic or basic it is. Now, you might think, well, wait a second, how does H plus affect being a base? Because I thought it was OH minus. Well, it turns out that these two things are related. And if you have the exact same amount of both of them, you end up with a neutral solution. But if you have lots of H plus in an acid, you have very, very little of this. Now, you don't have zero, is the thing. Because even if you have tons and tons and tons of H plus, there's still going to be some hydroxide out there just hiding, waiting to bonk into an acid and react with it. Likewise, if you were looking at a base, and you have lots of OH, you would have little of this. And so what we use, we measure H plus as our rubric. And so what we do is we put the amount of H plus into this formula. And the formula spits out a number from 0 to 14. Now, you can go below 0, and you can go above 14, but it's rare. You're not going to see it in this class. Except for maybe one example, now that I think about it. A solution with pH 7 is considered to be neutral. What that means is that there's the exact same amount of H plus and OH minus in the solution, and there's not very much of it. There's very, very little anyway. If the pH is below 7, what that means is that the solution is considered to be acidic. An acidic solution has a lot of H plus relative to, say, a neutral solution. And if I go the other direction, a solution with a pH higher than 7, we're going to call that basic. A basic solution has very little H+, which means lots of hydroxide. So now that we have the definitions out of the way, let's look at some examples of pH. Now, the first thing I do want to comment is that this chart that I got has a typo. This isn't 0 here. This should be 1. Now, if you look in the middle, you'll see water. Water is the definition of the midpoint of the pH scale. If you have as much acid as water it does, you are neutral. Now, depending on which direction you go, you will approach the acidic or the basic side, and you will get to gradually more and more dangerous things. So, for instance, going from water at pH 7 downward, we run into things like urine and milk. Urine is something you produce, so it's not hazardous. You just don't want it in your body forever. Milk is not hazardous. We consume it. Acid rain, not super dangerous because all water is acidified to some degree in the environment. Acid rain is actually pH 5.5, and that's just the rain you feel outside. Coffee is pH 5. Tomato juice is pH 4. Grapefruit and orange juice and soft drinks are pH 3. And you can start to see that these are starting to get a little more aggressive, right? Lemon juice and vinegar are pH 2. And then we just jump straight to stomach acid secreted from your stomach lining. And then battery acid. So yeah, like that escalated quickly, didn't it? Now, what is happening to the amount of acid, or H+, in each of these? Well, what is happening is that each time we go down a pH step, we increase the amount by a factor of 10. So pH 6 is not just like double the intensity, it is 10 times more acidic than pH 7. And pH 5 is 100 times more acidic than pH 7, or 10 times more acidic than pH 6. So each of these steps down is times 10 more acid. So what that means is that by the time you get to pH 1, you are 1 million times the acidity of water. And something with pH 0 would be 10 million times the acidity of water. Now, for reference, the acidity of water is this. 1 times 10 to the minus 7 moles per liter. This is at room temperature. So in order for something to have a pH of 5, you would have to have 100 times that number, or 1 times 10 to the minus 5. Now, you'll notice that these numbers are still really small until you get to about pH 1, where that would be 1 times 10 to the minus 1, or 0.1 moles per liter. So this would be 0.1 molar HCl, which we use in the laboratory. In fact, we use stronger stuff than that. We use stuff that's pH 0 in the laboratory, which is hazardous. Now, going in the other direction here, if I go from pH 7 to pH 8, what I'm actually doing is I'm dividing by 10. And if I keep doing that over and over and over and over and over again, I will eventually get all the way down to pH 14, which is something that has so little acid in it that it's all entirely base. And so you can look at the compounds that do that. So we go from water to baking soda, seawater and eggs, to toothpaste, to milk and magnesia, to something we would no longer put in our body. We do not drink household ammonia. Soapy water, bleach, oven cleaner, and Drano. Like, that escalates pretty quickly too, right? So the threshold of things that we consume, we tend to go towards the acidic side because the first thing that your body can hit, that anything you consume hits, is your stomach, which is acid, right? So if you put something like lemon juice in your stomach's going to go, oh, big deal. It's lemon juice. I'm already pH 1. What do I give a shit if it's pH 2 that you're giving me? But if you start drinking something like milk of magnesia, which is pH 10, then your stomach's going to go, well, wait a second, hold on here. This is not what we agreed upon, because now you are changing its pH significantly, right? And that's no good if you do it too aggressively. So if you drank, like, say, ammonia, that would be hazardous because, one, ammonia is not healthy for you because it's very reactive with other things. But two, it's such a strong base that you would neutralize all of your acid very quickly, and you could cause damage to your stomach lining, as well as like your esophagus and other things going down. Now, I don't know if you've ever heard of pH-adjusted water, and you may have heard of or seen videos online. There's this really infamous video of this woman teaching her daughter about pH balanced water, which is total pseudoscience and garbo. And they test the pH of all this different water, and like tap water ends up being like pH 5.5, and she's like, oh, I will never drink this, it's acidic. And I'm like, this is totally healthy for you. And they insist that you should only drink basic water of like pH 9. Total poppycock. Absolutely bullshit. And the reason for this is because, again, what's the first thing that your stomach sees? Or what's the first thing that anything that you consume sees? Well, it's your stomach. It hits pH 1. Anything you consume gets completely neutralized and changed to be pH 1. So if you are buying water that's been basicified, I guess we'll say, where people have changed its basicity to be like pH 9 or 10 or whatever, throw that shit in the garbage, because it's totally people are just trying to take your money. It doesn't do anything. All right. So that's an understanding of what the various things are on the pH table. Now our job is going to be, how do we calculate this? Oh, first I have some examples for you to try, though. So what I want you to do is, based on the information that I've provided you, I want you to tell me acidic, basic, or neutral for each of these descriptions. Okay? You type your answers in the chat. We'll go over the solutions together in 3 or 4 minutes. One more minute, we'll go over the answers. All right, so we know that anything with pH below 7 is acidic. So we can just label acidic, acidic. We also know that anything containing a molecule that splits into H plus and something else would be acidic as well. All right, and then all the basic things would be, would be higher pH than 7 or contain KOH. And then that leaves us with one thing in the middle here, and that's this guy. So pH 7 is neutral. All right, let me know if you have any questions. How do we calculate pH? The formula to calculate pH involves this function. What the hell? So there's a button on your calculator that says log. And what you need to do is you need to type in the amount of H plus or H3O plus. They're the same thing. In moles per liter. And then you push log on your calculator, and then you push minus to flip the sign of the number. Okay? So, depending on your calculator, let me see if I can simulate this. So, let's... Online TI 30X. Yeah, this will work. There we go. This kind of works. I don't know where the heck I am on the internet. I just went looking for one. All right, so if your calculator looks kind of like this, then what we would do to type in this number is... So first of all, this type of calculator has a display that retains all of my inputs. So what I can do is I can type in the formula that I want. So minus log, and now I type in the molarity of whatever. So if I wanted the molarity of water, that would be 1 times 10 to the minus 7. Oops, hold on. So, there we go. And then when I hit enter, I should get 7 as a result, because water is pH 7. And lo and behold, you do. Now, your calculator may not print stuff in a line like this. You may type in a number, and then if you hit a function, it applies that function. In that case, what you want to do is you want to type in the number first, then push the log button, and it will log the number you just had. and then push the negative sign because it will change the sign of what you have. Okay, so just as some more examples here. So negative log of, I don't know, a 0.350 molar solution would be about pH 1. 0.45 is what I got. So this is how you use log. Log is an exponential sort of thing. So if I take the log, for example, the log of 1 is 0. But the log of 10 is 1, and the log of 100 is 2. So as I keep going up by a factor of 10, the number that it spits out increases. Now, if I go down by a factor of 10, which would be 0.1, then I get negative 1 as my result. Log of 0.2 would be, oops, not 0.2, sorry, 0.01 would be negative 2, and so on and so forth. So it's just a different way of counting that is useful for various formulas. Now, we negative all of these logs, so taking the log of a decimal should give you a negative number, but then we negate the answer, once we've done that, to generate a positive number. So if I go negative log of a 0.01 molar solution, I don't get negative 2 like I did before, I get positive 2. So that's how the formulas work. So play around with your calculator, and what you should get are the same things that I'm getting as I do these problems. If for some reason you are not getting the right numbers, let me know. For example, try typing this on your calculator right now. Type in negative log 1 and hit enter, and you should get 0. And if you do that with negative log 4, you should get negative 0.6 as your answer. So don't use the button that says ln. ln is a different function. Now, what is the 10 for? The 10 means base 10. So that every time you increase by a factor of 10, the output would increase by 1. So that's, if I was doing like log base 2, then every time I increase by a factor of 2, excuse me, I would increase my output by 1. So log of 2 would be 1, and log of 4 would be 2, and log of 8 would be 3, as opposed to 10, 100, and 1,000. We're multiplying by 10 each time. All right, so if my acid that I am working with is a strong acid, then calculating the pH is very easy to do. The way that you do it is the following. All you do is, so if it's a strong acid, all you do is take the molarity of the acid and put it in the log equation, and you're all done. If it's a weak acid, I have to tell you something about it. So there are ways to calculate the amount of acid in a weak acid solution. However, it's math that is well beyond the scope of this class. It involves the quadratic formula. What? And we're not going to do it. So don't worry about that. I will give you the amount of H3O plus so that you know what to enter into your log equation. Likewise, I may give you an equation where I ask you, like, okay, here's pH, tell me H3O plus, so you could solve backwards. And we're going to do a few examples of that in a second. Now, the pH for a base can be calculated in a similar way if you know how much H plus is in there. However, if you know how much OH there is instead, you can calculate the pH in a different way. And so the way that this works is we calculate what's called the pOH. And for this, you just put in the molarity in moles per liter of the hydroxide. And that will give you the pOH of the formula. And then you use that in this formula here. 14 minus pOH equals pH. So let's do some examples and do some calculations here. So let's find the pH of 0.250 molar sodium hydroxide. So first thing we know is that this is a base, which means the pH should be high, right? Bases have pH higher than 7. So if we do our calculation, we get a number that's higher than 7, we're probably on the right track. If you get a number that's less than 7, we've probably made a mistake somewhere. So let's give this a try here. Now, because it's hydroxide... Oops, hold on. I got to get a color that's visible here. So I know that sodium hydroxide is a strong base. So for sodium hydroxide, I can trust that number and put it straight into the equation. But I don't know what this is, right? Well, fortunately, we have an alternative path. If I know the hydroxide instead of the H+, I can calculate the POH, which is negative log of OH minus. And so that would be minus log of 0.250, which you should type in your calculator just to see that you get the same thing that I do. And I got 0.602. Now you might be asking, how do you do sig figs for log? And the answer is that the number of decimal places that goes in is the number of decimal places, or the number of sig figs that comes out. So really, just however many sig figs you put in there, take that many out, and you'll be fine. Just treat it like it's multiplication. So we know that the POH is equal to 0.602 for this solution. Now I can go to say, okay, well, 14 minus the POH equals the pH. So 14 minus, and this is 14.000000 forever. So this is exactly 14. So when I do my subtraction, oops, not 13.5. 13.398. So the pH of my solution would be 13.398. Assuming I did my subtraction right. Yeah, that looks good to me. All right. Let's do another one. I want you to try this on your own. We'll do that one together on the bottom here. So I'm going to give you a weak acid, and I calculate for you that the weak acid concentration is 5.25 times 10 to the minus 5. What's the pH of the solution? Type that into your calculator and post your answer in the chat. We'll go over the answer together in a second. One more minute, we'll go over the answer. All right, so you should have typed in negative log 5.25 times 10 to the negative 5. And the answer that comes out is 4.28 pH. So if that's what you got, that's the right answer. Now, how do we undo... I just realized I need... Oh, and I can't get back to that page. No. Oh, wait. Hold on. Yay. Yeah, I need the calculator back. There we go. So for the next problem that I have here, let's suppose that you know the pH. How much acid is in there in moles per liter? How would you do this? Well, let's call back up the calculator. Loop. All right, so there's my calculator. All right, so how does this work? What's the opposite function of log? So let's put this over here. And the answer is... Here's my formula for pH. First, I got to move this minus over. So I'm going to put this minus here, and I'm going to erase it from this side. And then I'm going to do this function, 10 raised to the power of. So that cancels out that. I have to do the same thing over here. My formula becomes H3O plus equals 10 to the negative pH. So how do I type that in my calculator? So we've been using the 10 to the key for a while. However, you may need to use a different key than you've been using. So in this calculator right here, times 10 to the will still work if I go 1 times 10 to the. But instead, what we actually want to be using here, there should be a 10 to the x button. I'm trying to find it. Let's see here. Actually, I don't see it. So here's what we'll do. We'll go 10 to the power of negative pH. And so what's the pH of blood? 7.30. And I get this as my answer. And we're going to do this to that. There. Just to get more sig figs, because I just happened to run off the side of the screen there. So my concentration of H3O plus in the blood must be 5.01 times 10 to the minus 8 moles per liter based on that. So again, here's the formula that you need to turn a pH into a concentration of acid. Type in 10 raised to the power of negative pH. That'll give you the amount of acid in moles per liter. If you get a really tiny decimal that's only got 1 sig fig, you'll need to learn how to turn your mode into scientific mode so it spits out more numbers. All right. Last question you can do on your own. I don't think this is particularly difficult. Concentrated HCl is sold as 14 molar. What is its pH and pOH? You're going to get a number that is below 0 for the pH and a number that is above 14 for the pOH, and that's intended. So, all right. And there's the homework practice for this section. How were we on time? We'll get started on buffers, and then we'll take our break here. So, or actually, I do have a few more slides, because I do want to talk about other effects of pH besides, like, just numbers and stuff. So, why do we care about pH? Oh, you know what I can do? I can turn on... This calculator is kind of nice, though. I kind of like having this here. So, I might have to, like, find this page and download this app. So, why do we care about pH? Everything on Earth has a relatively neutral pH for the most part. So, the ocean is about pH 8 as of 2000. It's since gone down. Very unfortunate due to climate change. 20 years later, there's a lot of more CO2 in the water. The pH of rainwater is about 5.6 up here in the northwest, anyway. And if we measure the pH of the water in Edmonds, which is where I could find data when I wrote this slide, we find that the pH is approximately 7.4 to 7.6. So these are all relatively neutral things. If we expose stuff to acids or bases, we would greatly change the properties of the water that we are interacting with, and that could be bad depending on what we're working with. So things with high pH or low pH will affect the environment in significant ways. And sometimes that's interesting and sometimes that's calamitous. And so it's our job to understand how pH works and what we should be doing to keep the pH in the range that we want it to be. So, first of all, everything we do makes CO2. Every time you breathe, every time you turn on your car, every time you turn on anything in your apartment, all of that is coming from electrical power that is being generated by some sort of power producing facility. And if that power producing facility is not geothermal, wind, hydroelectric, or nuclear, odds are it's natural gas or oil or coal. That means that we burned something and made CO2, and there's now CO2 in the environment. Not your fault, it's just how our civilization is built around. We built our energy generation around CO2 production. That CO2 will interact with water in the atmosphere to form H2CO3, which is carbonic acid. This is a weak acid. This is the same acid that's in my fizzy soda, although there's more of it in the fizzy soda than there is in rainwater. So carbonic acid is a weak acid. It does not affect pH terribly much, which is why the pH only goes from 7 to 5.5. Not a huge deal. Now, the issue occurs when we get sulfur compounds in our atmosphere. So this would be things like SO2 and SO3. This is how acid rain forms. When you burn stuff that contains sulfur or nitrogen in it, the result that you get is SO2 or NO2. When those combine with water, you get H2SO3 or HNO3. You might remember HNO3 is a strong acid. H2SO3, is not a strong acid, but it is a precursor to sulfuric acid, which is a strong acid. As a result, when we make significant amounts of SO2 or NO2, the result in our rain is that the pH goes down very quickly. And I have here a picture of pH levels in rainwater across the United States in 1996. And what you can see is that all the green areas have pH 5.3 or higher. So that's the Midwest, the West Coast, because we're the best coast. It's all green everywhere. Green as far as the eye can see. Where is it very, very high pH? Where does America suffer from acid rain? It's almost perfectly centered around one place, and that place is Pittsburgh. I'm not joking. Pittsburgh is right here. smack dab in the center of that. What do they make in Pittsburgh that might cause acid rain? I'll give you a hint. Their football team's named after it. Very good. It's the Steelers, right? Pittsburgh is a steel town. They have a very heavy amount of steel industry, and steel is a very heavy polluting process because you have to smelt all these iron and coal containing mixtures, and in doing so, you produce lots and lots of CO2 to heat stuff up that hot. So the act of producing steel causes so much CO2 generation that it has affected the pH of the water there. In fact, I used to visit somebody in Pittsburgh. I would go over there all the time and be like, wow, everything is sooty around here. It's like I've stepped back into the industrial era, and it's because of the steel industry. It's like, it's huge. And a lot of the town is just dirtier as a result. Pittsburgh is still really fun, though. I really liked Pittsburgh. But as a result, it affects the pH of the rainwater because there's just such a heavy steel industry there. And in the surrounding area, it's not just Pittsburgh. Everywhere else around it too, because that's all where all of America's steel is made, is over on the East Coast. And as a result, we end up with interesting things like erosion. And by interesting, I mean kind of unfortunate, right? So erosion occurs when basic minerals, such as things like calcium carbonate, which is the substances that make up limestone and marble, things that you would make statues out of. Acid rain contacting this will cause these to slowly deteriorate over time. Now, it starts off by just getting smoother and you lose detail, but over time you would erode the very top layer to reveal the limestone beneath, and which is why you can see the white here, because the whole top layer has been eroded by what I would presume is that like acid rain has fallen on something which then landed like right here and then ran down here and down this person or the statue's face. And so you lose all that detail that went into this statue when it was created. And that's purely due to acid rain. Now, corrosion can also occur, which is the erosion of metals. And if acid rain contacts, say, your car or vehicle, then it is more prone to rust because acid accelerates the production of rust. So having a low pH is not particularly good, and it's very easy to do that if we aren't aware of what we are doing to the environment. So it behooves us to be environmentally responsible when we consider ways of making stuff. All right. Before we take our break, I'm just going to skip this section. We're not going to do salts. I just don't care. It's not on your exam. It's not on your final. I don't care about it. I do care about buffers, so when we come back from the break, it will be the last section of Chem 121. Oh, break is over. No, I'm just kidding. I got to reset that. Oops, I don't want to save my split. There we go. All right, we'll go get some more music, and I'll see you in a bit. All right, we're back. Let me just get this off the screen there. And let's talk about buffers. Now, it takes a very small amount of acid, excuse me, to change the pH of something. For instance, something that we could do is we could do a calculation to figure out how much soda pop would change your pH to be fatal. So, let's suppose that your soda is pH 2. And your blood is pH 7.35. Now, if I want to calculate how much H plus there is in my blood, we already did that calculation. I can do 10 to the minus pH, and we'll get the number. So 10 to the minus pH is 4.46 times 10 to the 8 is what I got. That seems different than the number I got before. Did I write a different number down? You know what would be able to tell me that, though? The calculator that I no longer have. Oh, because I did 7.330. This I wrote down 7.35. It's close enough. Okay. So this is the pH of your blood. What's or how much acid is in your blood? How much acid would be in something that was pH 2? Well, it'd be 10 to the negative pH, or negative 2, which is this. There's quite a difference between those two, right? So if I were to write these in as decimals, here's soda, and then blood. So you could imagine that a very small amount of soda would be needed to change this number significantly, right? Because there's really not that much acid in your blood, but there's tons of acid in your beverages and soft drinks that we consume all the time. In fact, the limit before you hit acidosis, so pH about 6.85 is deadly. If you go past this. So the limit for this would be if you had this much in your bloodstream. 10 to the negative pH, 6.85. So if you go above this amount, so we'll say limit or so, 3, 4, 5, 6, 7. If you go above that amount, that could be dangerous. And soda is way over here. So What the heck? How much soda would be needed to screw up your bodily chemistry completely irreversibly if we didn't have a way to mitigate it? And the answer is something on the order of like milliliters. Like you could drink like a milliliter of soda and it would be fatal. Like you would die because of acidosis. But this doesn't happen. In fact, you have all the stomach acid in your stomach that doesn't affect the rest of your body either, because your stomach acid is in direct contact with your intestinal tract, which is just a thin line of mucous membrane between all of this acid and your bloodstream, which is where all your nutrients get absorbed in your belly, right? So how the heck does this work? And the answer is buffers. Buffers are responsible for resisting changes in pH. And how do they do that? They do this in the following manner. Okay. Now, here's the range of pH that you're allowed to be in for your body, although you need to stay very close to 7.35. Below 6.8 or above 7.8 is deadly, and you die very quickly, like incredibly quickly. This is a medical emergency if you have a pH that is too low or too high. So how do we deal with this in the bloodstream naturally? And the answer is that we have a buffer that resists the changes in pH. So the definition of a buffer is a series of chemical reactions that are put together to resist changes in pH. Now, buffer is made of two things. A buffer must contain a weak acid and its conjugate base. We're going to see that in action in this video here. We're going to make a buffer by adding a solid base and then adding acid to it until it becomes a buffer. If this is the video that I'm thinking of, let me see here. Oh, it's not. Okay, I have a different video, and this one's actually better. All right, so on the screen, what you can see here is two solutions that have an indicator added to them. And you can see that the indicator has a color key. The key is shown in the middle here. So green is a roughly pH 8. So this is just water with the indicator added to it. This is just water with the indicator added to it, but we've also added a buffer. And so what we're going to add first is we're going to add acid to the distilled water. What you're going to notice, we don't need the music here, is that it only takes like 1 or 2 drops. So 1 drop of acid, and what happens to it? Whoa, the pH went from 8 to 1. So that's a large quantity of fluids to be completely changed by 1 drop. And so we'll do that to the buffer here. So he added 2 drops here. You'll notice that nothing's happening. That's because the buffer is resisting the change in the pH somehow. How does it do it? It's a mystery. Nobody knows. Maybe you'll figure it out. No, we're going to talk about that in a little bit. But how much acid do you actually need? So he's going to just keep stirring this and adding it, and you're going to see it slowly progress through the colors. So it's less green than it was when it started now. And he's already on his 3rd pipette full, so drip, 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 drip. He's having to add all of this acid to this buffered solution just to get it off of green. So now it's kind of yellow. And he already ran out of acid in the pipette, so you get the point, right? Alright, so the next thing he's going to do is he's going to add base. Oh no, he's going to keep trying to acidify it, I guess. Yeah, keep trying, man. It's going to take a while. Let's see here. Let's see if we could speed this up. Playback speed. Double. There we go. He finally did it. Well done. Okay. So now what he's going to do is he's going to add base to this. And when you add base, it should increase in pH, so the color will go towards blue, according to the indicator chart. Now, in the unbuffered solution, which again is just water, let's see how long it takes for this to happen. So, there we go. 1 drop. Boop. All the way to blue. So, the solutions that we're using are very powerful. Oh, now it's green again. So 1 more drop, and now it's just going to be, it's going to be dark blue. pH 12. There you go. So you can notice that the unbuffered solution takes very, very little substance to completely wreck its pH. And if this was your bloodstream, 1 or 2 drops would kill you. Every substance that you interact with would be fatal. But fortunately, we have buffers, and buffers resist changes in pH. So this has already taken, like, I'm trying to count the drops as I talk. So that's 15, and we're back to yellow. 16. He speeded himself up. I didn't even have to do it that time. I can't count the drops now, but like it's clearly taking a while. Now the buffer is not perfect. It does not allow you to put infinite acid or base in there to resist the pH. However, it is quite effective, and we're going to see why as we explore this section here. So again, the 2 things that you need for a buffer are a weak acid and its conjugate weak base. You must have these 2 things in order to have a buffer. If you have a weak acid and any other weak base, you get a salt. You do not get a buffer. The buffer will not work. So for instance, I could use H2CO3 because that's a weak acid, and its conjugate base, which would be this minus an H+. This would be a buffer, because I have a weak acid and the conjugate weak base. What about something like HBr? Could I use HBr and Br minus? They're conjugates, but this is a strong acid. So this will not work and will not form a buffer. You must use a weak acid and its conjugate base. Here's a common buffer that is used in biology. This is called the phosphate buffer. This is the buffer that regulates pH within your cells, keeping them at about a pH of 7.35. So you have H2PO4-, which is monosodium phosphate, or monosodium hydrogen phosphate, or you might call it basic phosphate. HPO4 2- is called dibasic or disodium hydrogen phosphate. There are many common names for these. But together, those 2 conjugates make the phosphate buffer. Now remember, the difference between a conjugate acid and its conjugate base is just H+. So if you choose a weak acid, all you gotta do is strip away its H+, or one of the H+, and you will get the conjugate base. So on the screen here, I have a bunch of things. I want you to tell me buffer or not a buffer. And if you have one that is not a buffer, tell me why. I'll give you 5 minutes to think about it. We'll go over the answers shortly. All right, one more minute. We'll go over the answer. All right, so let's look at this first one. If they differ by just H plus, then they're conjugates, and if one of them's the weak acid, the other one will be a weak base, and that will fulfill the qualifications of a buffer. So these two differ only by H plus, and acetic acid is a weak acid, so this will make a buffer. So buffer. Now the second one won't make a buffer because even though these are conjugates, HCl is a strong acid. So the second one doesn't make a buffer. What about the third one? Well, these aren't conjugates of each other. They are weak acids and bases, but they're not conjugates. Instead, this makes a salt, which is no good. You don't want salt. And then finally, are these two the same thing? Well, we have to break them into their ionic compounds. So we got sodium, which we don't care about, and bicarbonate, which we do. And then we've got sodium, again, don't care about it. And so we want to compare these two. Are they conjugates and are they both weak? And the answer is yes, so this makes a buffer. Bicarbonate is the conjugate of carbonate. They differ only by H plus. All right, so now all we have to do is study how this works. And to do that, oops, I hit the wrong button. We're going to use our phosphate buffer here. And so what we're going to do is we're going to add strong base to it. So strong base is hydroxide. So here it is. Here is the status of our buffer. Our buffer is normally this. Now, what ends up happening is if I put a strong base into the buffer, it will react with the weak acid. And the result that we make is we make a weak base. So instead of the strong base being in the solution, which changes the pH rapidly, it instead immediately reacts with something and produces more of this, which already existed in the buffer anyway. So we have taken the OH minus and tied it up by reacting it with the weak acid. And in doing so, we produce more weak base, which was already in the solution anyway, so the pH change is negligible. Now, we could do the same thing if we added strong acid. So here is our strong acid being added. The strong acid is going to react with the weak base part of the buffer. And because it gets tied up in the buffer now, forming a weak acid, the pH remains more or less the same. Instead of going down a lot, it goes down a very small bit. So this is how buffers retain pH at a constant or nearly constant level. Any added acid that comes along will react with the basic part of the buffer, creating more acidic part of buffer. Since the acidic part of the buffer is already there, adding more of it doesn't change the pH very much. Likewise, if I have any base that comes along, it will react with the weak acid part of the buffer to consume the strong base and neutralize it. So that all we have are the same weak acids and weak bases that we started with, and so our pH remains roughly the same. And because of this, we can stay alive quite effectively. So, again, strong base will react with the weak acid, strong acid will react with the weak base, and these reactants just cause our components of our buffer to interconvert between one and the other. Now, you can't do this infinitely. If you add too much strong acid or strong base, what will happen is that you will overwhelm the buffer. A buffer is a mixture of both weak acid and weak base. But if you add so much weak acid that you completely use, or I'm sorry, if you add so much strong acid that you completely use up the weak base, and all you have is a weak acid now, it's no longer a buffer. Now it's a weak acid. So if all of one component of the buffer gets consumed, the buffer is ruined. And then adding extra stuff in there, there's nothing to consume the added strong acid or base. The pH would then sharply change. So you may actually see things that look like pH curves. And so what those pH curves look like generally is, oh, here's my buffer region. I'm going to keep adding acid to ruin it, or adding base to it, and then suddenly the pH does this. So buffers resist changes in pH. So pH was on the y-axis here. So you may see a diagram like that in your textbook or in other places. We're not going to deal with those pH diagrams. So I'm going to do these problems with you, since I think there's only like one person watching right now anyway. Two, maybe. So we're going to show how this buffer reacts with each of these things. Okay, so first let's write the buffer reaction. So I have my weak acid, which is H2CO3, and my weak base, which is bicarbonate, sorry. And these can go back and forth. Now, if I'm going to add a small amount of HCl, HCl is a strong acid, which means I'm adding this to the solution. Which component will react with H plus to go back to the other thing? Well, it's this one, right? It's even written right there. So if this is my strong acid that I'm adding, it will combine with my bicarbonate to form carbonic acid. And the buffer neutralizes the acid by just making more weak acid. But if I added hydroxide instead, which is a strong base, which part of the buffer will react with that? Well, it will be the carbonic acid part, because it's the weak acid. This is my strong base. It will react and we will make bicarbonate again, which is just the weak base that is in my solution. So the products, again, are things that already existed in the buffer. So we have basically neutralized the added H plus or hydroxide. You can't see what I went up and highlighted, but it was this up here. All right, that's how a buffer behaves. If you have questions, let me know. All right, the last thing that you must do is celebrate. Oh, I had one more question, I guess, on here. Where do you think the body gets carbonic acid or bicarbonate to create this buffer? Turns out it's from respiration, just in case you were curious. So when you breathe, you consume oxygen, and you would normally breathe out CO2. But some of that CO2 stays in your blood anyway. And so that's where your buffer comes from. You can get rid of that if you have too much of it, because you've neutralized too much stuff, maybe, for example, by exhaling it. And so that's where like hyperventilating can come in, where you have too much CO2 or maybe even too little CO2. There's the homework practice. There's only like 11 problems on that. All right, now you get to celebrate. That's it. There's no more content. Hooray! If only there was someone here to celebrate. But there's not, so I guess I'll just leave it at that. All right, we're gonna end the lecture early, 30 minutes early, because I'm out of stuff to talk about. So what we're gonna do tomorrow is the review session for exam number 2. Exam number 2 is chapters 6 through 10, including everything up till this point. Okay. So make sure you are covering the chapter 10 content this week. There are a few questions on it on exam 2. You will see those on Friday. Tomorrow will be the review session. You may ask me any questions about anything you want from chapters 6 through 10. I'll be happy to go over it during the 2-hour period that we have tomorrow. Make sure that you get quiz number 9 in tonight. It is due. Make sure you do the course evaluations. Make sure that you do lab worksheet number 5 next week. And very, very, very important, make sure that you do exam number 2 this week, okay? More on the exam and an announcement, as well as at the review session tomorrow. Hope to see you there. Have a good night, and thanks for coming to Chem 121.